Okay, I hope I'm audible to all my students who are attending this particular lecture for the EC2C4-Econometrics-2 course. If all students can recall that in the previous lectures, we were solving some problem sets. We had started our discussion of problem set 1 in the previous lectures, and we had completed problem set 1 for discussion. Now, in this particular lecture, I'm going to start with the discussion of problem set 2. So for all those students who have taken up EC2C4 Econometrics 2 course, we are going to start with the discussion of problem set 2 in this particular lecture. And I'm going to solve problem 1 completely in this particular lecture. So let's quickly start with this particular lecture. So question 1 is taken from the book Woolrich, chapter 2, which is problem 8. Let's quickly look at this particular problem. Consider the following simple regression model y equals beta naught plus beta 1x plus mu. Okay. Given the so-called Gauss-Markov assumptions, sample linear regression 1 through sample linear regression assumption 5, the usual OLS estimators beta naught hat and beta 1 hat are unbiased for their respective population parameters beta naught and beta 1. We already know that. Let beta 1 tilde be the estimator of beta 1 obtained by assuming that the intercept is 0. So when we take the intercept as 0, then the OLS estimator we get is beta 1 tilde. Okay. So part 1 asks us, find expected value of beta 1 tilde conditional on x1 to xn in terms of xi's, beta naught and beta 1. Verify that beta 1 tilde is unbiased for beta 1 when the population intercept beta naught is 0. Are there any other cases where beta 1 tilde is unbiased? So let's first of all work out what will beta 1 tilde be, and then let's show whether it's unbiased and what are other possible cases where it can be unbiased. So let me quickly come to the whiteboard to solve this particular problem. Okay, so I'm just writing the main heading for completeness. We are looking at EC2C4 Econometrics 2 course offered at London School of Economics and Political Science. And in this particular lecture, we are looking at discussion of problem set 2. So let's look at question number 1, where I'm quickly writing what is given. So for the regression model y equals beta naught plus beta 1x plus u, when I conduct OLS on this particular model, I get beta naught hat and beta 1 hat. This is my sample intercept. Which is an estimator of beta naught, which is an estimator of the population intercept beta naught. And then I have beta 1 hat, which is the slope sample slope coefficient. Sample slope coefficient, which is the estimator of the population slope coefficient beta 1, which is the estimator of the population slope coefficient beta 1. What else are we given? We are given that beta 1 tilde is the estimator of beta 1 when the intercept is 0. When the intercept is assumed to be 0. That is, what is the intercept? Intercept is beta naught. I assume it to be 0. So corresponding to it, what will my sample regression function be? So my sample regression function in general is y is equal to b0 plus b1 x I plus ei. Okay, so this is my sample regression function. So putting B0 equal to 0, because we are given that B0 is equal to 0. We are given that beta naught is equal to 0. If beta naught is equal to 0, if my population intercept is equal to 0, I can write that therefore y is equal to B1 xi plus ei. So what will ei be? yi minus B1 xi. This is going to be my ei. Remember, I have put B0 as 0 because we are assuming that beta naught is equal to 0. So I can say since beta naught is equal to 0 and B0 is an estimator of beta naught, B0 is an estimator of beta naught, therefore we say that B0 is equal to 0. I put B0 as equal to 0 in the expression. Now for OLS, our objective is what? Our objective is to minimize summation EI square, which is I need to minimize summation yi minus B1 xi square. What do I need to choose? I need to choose B1 to minimize this. Let me write it clearly. I need to choose B1 to minimize this. So we look at the first order condition. Now if I erase all this off in the beginning, so my first order condition is del summation ei square over del b1 equal to 0 implies if I partially differentiate this with respect to b1, I get summation. The derivative is going to be 2 times yi minus b1 xi times internally the derivative of yi minus b1 xi with respect to b1 is minus xi equal to 0. So 2 into minus, I can take minus 2 outside the summation times yi minus b1 xi times xi is equal to 0. Minus 2, I can take it to the right hand side, it will vanish. So I have summation yi minus b1 xi. So if I open up the brackets, let me open up the brackets, it's going to be summation yi into xi minus b1 xi into xi is xi square equal to 0. If I open up the brackets, it's going to be summation yi xi minus b1 summation xi square equal to 0. Okay. So if I erase all this off, let's solve for b1. That is going to give us beta 1 tilde. So this implies summation yi xi is equal to b1 summation xi square, which implies summation yi xi over summation xi square is equal to b1, which I call as beta 1 tilde. Remember in the question, if I come back to the question problem set again, see, beta 1 tilde is going to be the estimator of beta 1, which we obtain by putting the intercept as 0. That means what I've got by conducting the OLS procedure, the B1 I've got is nothing but beta 1 tilde. So this is my answer for beta 1 tilde. So I can erase all this off and I can write that therefore beta 1 tilde comes out as summation as I goes on from 1 to n yi xi over summation as I goes on from 1 to n xi square. This is beta 1 tilde. Okay, now what is the next part of the problem set asking us? So we now need to find expected value of beta 1 tilde conditional on x. So if I come back to the whiteboard, I can write therefore the expected value of beta 1 tilde conditional on the x's is going to be summation as I goes on from 1 to n. Now everything has to be in terms of x's. So can I plug in the value of yi? What is yi, guys? Remember, yi itself is beta naught plus beta 1 xi plus ui. This is my true regression equation. So plugging it, I plug in the value of yi as beta naught plus beta 1 xi plus ui times xi. It's getting multiplied by xi whole divided by summation as I goes on from 1 to n xi square. This is how we solve it. I just plugged in the value of yi as beta naught plus beta 1 xi plus ui. Okay, now if I erase all this off, I'm erasing the whole calculus part off now. And let me continue with the solution on the top. I can write therefore beta 1 tilde is gonna be summation as I goes on from 1 to n beta naught into xi plus beta 1 xi square plus ui xi whole divided by summation as I goes on from 1 to n xi square. This is what I get. So if I open up the brackets of the summation, for which let me erase this particular part off. So this becomes beta 1 tilde is equal to beta naught times summation as I goes on from 1 to n xi plus beta 1 times summation as I goes on from 1 to n xi square plus summation as I goes on from 1 to n ui xi whole divided by summation as I goes on from 1 to n xi square. Okay, and now I can further write it as beta 1 tilde is equal to, if I separate the terms of the numerator, it's beta naught times summation as I goes on from 1 to n xi over summation xi square plus beta 1 times summation as I goes on from 1 to n xi square over summation as I goes on from 1 to n xi square plus summation as I goes on from 1 to n ui xi over summation I going from 1 to n xi square. Now this and this cancel out. I can finally erase the initial part and I can write the answer on the top. My beta 1 tilde comes out as beta naught times summation as I goes on from 1 to n xi over summation as I goes on from 1 to n xi square plus beta 1 plus summation as I goes on from 1 to n ui xi over summation as I goes on from 1 to n xi square. Okay, so now what do I need to do? I need to now show that beta 1 tilde is unbiased and we are given that beta naught is equal to 0. Remember, if I come back to the problem set, we are given that the population intercept beta naught is 0. And I need to check, I need to verify that beta 1 tilde is unbiased when beta naught is equal to 0. So if I come back, so I can write that expected, so I can write to show, I need to show that expected value of beta 1 tilde will be equal to beta 1 when beta naught is equal to 0. This means that beta 1 tilde is unbiased. So let's take the expectation operator. Expected value of beta 1 tilde is going to be the expected value of this whole big term. I can just write it. This is beta naught summation xi over summation xi square. Now, students, I'm getting rid of I going from 1 to n. We all know that I goes from 1 to n. So I'm saving on some time. So I just took expectations on both sides of this equation. So this implies expected value of beta 1 tilde is going to be beta naught times expected value of summation xi over summation xi square plus expected value of beta 1 plus expected value of summation ui xi over summation xi square. Remember, expectation of a sum is the sum of expectations. So expected value of this plus this will be equal to beta naught as a constant comes out. Expected value of this plus expected value of this plus expected value of this. Now, students can see this is going to be beta naught times. Remember, my xi's are non-stochastic variables. They take fixed values. So that means expected value of summation xi over summation xi square will be the same because it's going to be constant. Summation xi over summation xi square plus, again, beta 1 is a constant, expected value of a constant is the constant itself, plus summation xi square is a constant, it comes out. So 1 over summation xi square, 1 over summation xi square times, I can write summation xi times expected value of ui conditional on x. Or I can just write, for the time being, I can just write summation xi ui, summation ui xi, let me correct myself. Summation ui xi, or since we have taken expectations, guys, I can slightly correct this and I can write, this is going to be summation. Again, xi is non-stochastic, so it comes out of the expectation. So I can write summation xi times expected value of ui conditional on x. So this is what I get as expected value of beta 1 tilde. I'm revising it. It's beta naught times expected value of this is this itself because it's a constant, plus expected value of beta 1 is beta 1 plus 1 over summation xi square times summation xi times expected value of ui conditional on x. Remember, ui's are stochastic. They have a probability distribution attached to them. Xi's are non-stochastic. They take fixed values, so the expected value of them will be, the expected value of xi will be xi itself. So xi is going to come out. Okay, so if I erase all this off in the beginning, I can write expected value of beta 1 tilde is equal to beta naught times summation xi over summation xi square plus beta 1. Now, guys, this is 0. Remember, recall that expected value of ui conditional on x is equal to 0. One of the assumptions of the classical linear regression. So this is my answer for expected value of beta 1 tilde. And since beta naught is equal to 0, I can write expected value of beta 1 tilde will just be equal to beta. So hence, I can show that beta 1 tilde is an unbiased estimator of beta 1 when beta naught is equal to 0. This is what we had to show. When beta naught is equal to 0, expected value of beta 1 tilde is equal to beta 1. Therefore, beta 1 tilde is an unbiased estimator of beta 1. So, hoping all students have understood this. This is one case. When what's the another scenario in which beta 1 tilde can be an unbiased estimator of beta 1? Let's call this as equation star. So, if I erase this part off, so I can write that from equation star, beta 1 tilde can also be an unbiased estimator. It can also be an unbiased estimator of beta 1 provided summation xi is equal to 0. If summation xi is 0, one case is beta not equal to 0. That again makes beta 1 tilde as an unbiased estimator of beta 1. Another case is where summation xi is 0. When summation xi is 0, then also expected value of beta 1 tilde will be equal to beta 1. So summation xi equal to 0 implies x bar is equal to 0, because remember x bar is what? X bar is summation xi by n. So when summation xi is 0, it means x bar will also be 0. So there are two cases in which beta 1 tilde can be an unbiased estimator of beta 1. One is where beta naught is equal to 0. This was given to us. Another possibility is that beta naught is not equal to 0, but summation xi is equal to 0. If summation xi is 0, then also expected value of beta 1 tilde will be equal to beta 1, in which case beta 1 tilde will be an unbiased estimator of beta 1. So if I come back to the problem set, this is what the problem set was also asking us. Are there other cases where beta 1 tilde is unbiased? Yes. This is the case where summation xi is equal to 0. So hoping all students have understood how we have solved this particular problem and have no doubts. Let's look at part 2 now. Find the conditional variance of beta 1 tilde conditional on x1 to xn. So let's quickly come back to the whiteboard. Let's find the variance now. So if I erase all this off. So remember students, my beta 1 tilde had come out as what? Let me write the expression again for all students. Our beta 1 tilde had come out as beta naught times summation xi over summation xi square plus beta 1 plus summation xi ui over summation xi square. I'm not writing, but you all know that I goes from 1 to n. Okay. Now, what will variance of beta 1 tilde be? So, variance of beta 1 tilde conditional on x is going to be variance of this whole expression, beta naught summation xi over summation xi square plus beta 1 plus summation xi ui over summation xi square. This whole is conditional on x. This whole is conditional on x. This I can write as, now guys, this is non-stochastic variance. So this is a constant. Variance of this is 0. So I can write all this. Variance of beta naught summation xi. First of all, let me just open up the variance. So variance of beta naught summation xi over summation xi square plus variance of beta 1 plus variance of summation xi ui over summation xi square conditional on x. Now this is 0, this is 0 because beta naught, beta 1, xi's, these are all constants. Okay. Summation xi and summation xi square are going to be constants because xi's are non-stochastic variables. They take fixed values. There's no probability distribution attached to the xi's, remember. So we are just left with this expression. Now again, summation xi square is a constant. It comes out with a square. So 1 over summation xi square whole square. Recall that variance of ax is a square times variance of x. Recall this, where a is a constant. In this case, summation xi square is a constant. It comes out with 1 over summation xi square whole square times variance of the term in the bracket, which is summation xi ui conditional on x. Okay, this I can further write as 1 over summation xi square whole square times Variance of a sum is the sum of variances because summation xi, ui are all independent random variables. So I have summation times variance xi, ui conditional on x. Variance of a sum is the sum of variances because xi's and ui's are independent random variables. Okay. So this I can write as 1 over summation xi square whole squared up. And again, this is going to be summation variance of xi ui. Now again, students, xi is a constant, so comes out with xi square times variance of ui conditional on x. And recall that variance of ui conditional on x is equal to the homoscedastic variance sigma square. Remember, this xi is a constant. It comes out again of the variance. It comes out as xi square because of a square. So xi square variance of ui conditional on x and variance of ui conditional on x is equal to sigma square. So if I erase this initial part off, I can write that variance of beta 1 tilde is going to be, it is going to be 1 over summation xi square squared up times summation xi square times variance of ui conditional on x is sigma square. Okay. Now sigma square is a constant. It will come out of the summation. So sigma square times summation xi square over summation xi square whole squared up. This cancels with the power. So what do I get? Sigma square over summation small xi square. This is variance of beta 1 tilde. This is what we had to find out. Okay, so hoping students have understood this. So I can finally write my answer now. If I erase all this off, I can write that variance of beta 1 tilde conditional on x comes out as sigma square over summation as I goes on from 1 to n xi. Okay, now let's look at what the next part is asking us. Coming back to the problem set, show that variance of beta 1 tilde is less than or equal to variance of beta 1 hat. And we are given that there's a hint given to us that summation xi square is greater than or equal to summation xi minus x bar square. We all know that summation xi square is greater than or equal to summation xi minus x bar square. Unless and until x bar is 0, but x bar is not 0. Okay, so let me quickly come to the whiteboard. Now this is variance of beta 1 tilde. What is variance of beta 1 hat? Remember, for my regression equation, yi equals beta naught hat plus beta 1 hat xi plus ei, where this is my sample regression function. What is variance of beta 1 hat using OLS? For a simple 2-variable linear regression model with the intercept term beta naught hat not equal to 0, when I conduct the OLS procedure, we had learned the formula from my theoretical lectures on linear regression. Variance of beta 1 hat conditional on x, I can just write this part also. Variance of beta 1 hat conditional on x is just sigma square over summation as I goes on from 1 to n xi minus x bar square. This is something which students can find from my lectures on linear regression. From my lectures on linear regression, LR. So this is variance of beta 1 tilde conditional on x. This is variance of beta 1 hat conditional on x. And since we are given in the question that summation xi square is greater than or equal to summation xi minus x bar square. So this implies 1 over summation xi square. If I take the reciprocal, the sign of the inequality will change. So 1 over summation xi square will be less than equal to 1 over summation xi minus x bar square. If I take the reciprocal, the sign of inequality changes. Instead of being greater than equal to, it now becomes less than equal to. And now if I multiply sigma square on both sides, multiplying sigma square on both sides. What do we get? Sigma square over summation xi square is less than equal to sigma square over summation xi minus x bar square, which implies what is this? Variance of beta 1 tilde less than equal to what is this? Variance of beta 1 hat. So I have shown that variance of beta 1 tilde is less than equal to variance of beta 1 hat, where this is the formula for variance of beta 1 tilde we have derived. This is the formula for variance of beta 1 hat, which students can find from my lectures on linear regression. Since we were given this in the question, I use this to solve the inequality. I take reciprocal on both sides, I multiply by sigma square, I get the required answer. This is what we had to show. Okay, coming back to the problem set, let's look at the last part. Comment on the trade-off between the bias and the variance when choosing between beta hat and beta 1 tilde. So when I have to choose between beta 1 hat and beta 1 tilde, we need to show that there's a trade-off between bias and variance. So if I come back to the whiteboard, erasing all this off for part 4, okay, I'm just writing first of all that variance of beta 1 tilde had come out as sigma square over summation xi square, and variance of beta 1 hat, all these are conditional on the x's, has come out as sigma square over summation xi minus x bar square. Okay, now to compare beta 1 tilde and beta 1 hat, we use the formula for mean square error. We basically compare the mean square error of beta 1 tilde and beta 1 hat. So what is the formula for mean square error? Again, I've done this in my lectures on linear regression. Mean square error is the bias of the estimator. It is the bias of the estimator square plus variance of the estimator. Bias of the estimator square plus the variance of the estimator. Okay, now if I look at beta 1 hat, which we obtain from OLS, is unbiased. So that means the bias of beta 1 hat, is equal to 0. But if you look at the variance, we have just shown from part 3 that variance of beta 1 hat is greater than variance of beta 1 tilde. This is from part 3. So see, there's a trade-off. Even though beta 1 hat is unbiased, but its variance is high. Beta 1 hat is unbiased, that means this is 0, but this is high. On the other hand, if I look at beta 1 tilde is biased. But variance of beta 1 tilde is less than variance of beta 1. So the problem with beta 1 tilde is it is biased, but the good thing is it has a lower variance compared to beta 1. Now what is the bias of beta 1 tilde? The bias of beta 1 tilde is going to be expected value of beta 1 tilde conditional on x minus beta 1. Now what was this coming out? Remember, expected value of beta 1 tilde conditional on x. So students should be able to recall this equation. Recall, you must have written this a few minutes back, that expected value of beta 1 tilde conditional on x had come out as beta naught summation xi over summation xi square plus beta 1. So this implies expected value of beta 1 tilde conditional on x minus beta 1. If I take this to the left hand side, what do I get? Beta naught summation xi over summation xi square. That means expected value of beta 1 tilde conditional on x minus beta 1 comes out as beta naught summation xi over summation xi square. This is the bias of beta 1 tilde. Okay, and what I can do to make it more clear, to make it more systematic, I can divide the numerator and denominator by n. So if I erase all this off, if I erase the initial part off, so I can write that the bias of beta 1 tilde is going to be beta naught times summation xi by n over summation xi square by n. So this is going to be, what I've done is dividing the numerator and denominator by n. Dividing n for numerator, d for denominator by n in equation 1. Let's call this as equation 1. So in equation 1, I divide this by n, I divide this by n. Now summation xi by n is x bar times this I can write as summation xi square by n as it is. Now let's look at the bias of beta 1 tilde. Okay, so suppose I keep beta naught and summation xi square by n constant. So if I erase all this off, so first of all, did students understand that beta 1 hat is unbiased but has a larger variance? So I can write it here just for clarity that beta 1 hat is unbiased but has a larger variance, but has a relatively larger variance. Whereas beta 1 tilde is biased but has a relatively smaller variance. Hence, I can say there is a trade-off between, the bias and variance. You can see that there's a trade-off between bias and variance. Now, if I look at this case 1, case A, let me take case A, okay? Holding beta naught and summation xi square by n constant. That means, guys, I am holding this constant and I'm holding this constant. Let's look at the impact of an increase in x bar. As x bar increases, you can see that bias of beta 1 tilde increases, but I can say variance of beta 1 hat, which is sigma square over summation xi minus x bar square, also increases as x bar increases. You can clearly see as x bar will increase, this whole denominator will decrease. If the denominator will decrease, the whole term will increase. You can clearly see again there's a trade-off. As x bar increases, beta naught and summation xi square by n are constants, assumed to be constants. As x bar increases, bias of beta 1 tilde will increase. As x bar will increase, bias of beta 1 tilde will increase. But variance of beta 1 hat will also increase. So again, we have to choose between the two. Should we compromise on bias or should we compromise on higher variance? Because there's a trade-off between the two. As we increase x bar, beta 1 tilde will continue to become more biased. But then variance of beta 1 hat will go up. So beta 1 hat will estimate beta 1 with lower precision. I have a choice. What should I do? Should I prefer less bias with higher variance, or should I prefer higher bias with lower variance? Okay, so similarly, case B. Case B is holding x bar and summation xi square by n constant. So now, basically, what is kept constant? I am showing it here. So guys, x bar is constant in green color, summation xi square by n is constant, and suppose beta naught goes up. Or not goes up, suppose beta naught gets closer to 0. Suppose beta naught gets closer to 0. So I can say, I can erase this and I can write that beta naught is tending to 0. Not exactly 0, becomes closer to 0. Then students can see that bias of beta 1 tilde will decrease. And the good thing is, nothing will happen to variance of beta 1 hat, because variance of beta 1 hat does not include beta naught. And nothing happens to beta naught, variance of beta 1 hat. Nothing happens to variance of beta 1 hat, since variance of beta 1 hat does not depend on beta naught. It does not depend on beta naught. You can clearly see variance of beta 1 hat does not include beta naught at all. So that means in this case, beta 1 tilde is better. So beta 1 tilde is better for case B. It's better than beta 1 hat. Why is beta 1 tilde better than beta 1 hat? Because when beta naught is getting closer to 0, when this expression in yellow color, when beta naught is tending to 0, bias of beta 1 hat will continue to fall. So beta 1, bias of beta 1 tilde, let me correct myself. As beta naught is getting closer to 0, bias of beta 1 tilde will continue to drop to 0. And nothing is happening to variance of beta 1 tilde, variance of beta 1 hat. Nothing is happening to variance of beta 1 hat, because variance of beta 1 hat does not include beta naught. So in that particular case, for beta naught tending to 0, I can say for beta naught tending to 0, bias of beta 1 tilde will tend to 0, and variance of beta 1 tilde will be less than variance of beta 1 hat. So given both these situations, beta 1 tilde is a better estimator than beta 1 hat for case B. For case A, I can't say anything, because for case A, when X bar was going up, beta 1 tilde was becoming more biased, but beta 1 hat was having a higher variance. So again, I was facing a trade-off. In case B, I am not facing any trade-off, because holding X bar and summation xi square by n constant, when beta naught is getting closer to 0, beta 1 tilde is having a lower bias. Its variance is still less than the variance of beta 1 hat. So in both the cases, beta 1 tilde will be a better estimator than beta 1. Okay, so this is where I stop in this particular lecture. We are completely done with all these 4 parts in this particular lecture, and question 1 is over. In the next lecture, I'm going to look at question number 2 from problem set 2 for the EC2C4 course. So I stop in this lecture. I hope students have enjoyed this lecture. Any doubts? You can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolof economics@gmail.com. This is where I stop in this lecture.